Hi, and welcome to a new video. So in this video, we're going to be giving the problem statement for the valid anagram problem. So we're going to be covering the valid anagram problem. So let's have a look at the problem statement and what it says. So we're given two strings s and t, and we want to write a function to determine if t is an anagram of s. So what does an anagram really mean? Well, to put it shortly, an anagram is basically a permutation of another word. So let's have a look, okay? We have the word anagram, okay? And we have another word here, specified here, like nagaram, okay? We can see that these two words are very close together, and by close I mean I can sort of reorder or permute. So to make it more mathematical, I can permute this word, change the ordering of some of the letters so that I get this to get this algorithm to get this word right here. So if this is S and this is T, then I need to change S somehow, the ordering of the letters. I won't change any of the letters. I just want to change some of the ordering of the letters. So let's say I can switch N and A here to get N-A-A-G-R-A-M, right? And then I can swap G and A to get, let's write it here, to get N-A-G-A-R-A-M. And then I've got the required T. So basically I've just switched a few of the words and I've gotten the required word. So in this section, really, we're going to be given so many different algorithms to solve this problem. So we will first give an O(n) factorial algorithm. So the O(n) factorial algorithm is pretty bad, actually. An O(n) factorial algorithm really doesn't scale well, and the best you're gonna have is really, n can at most be, 10 or /11-ish. Any n bigger than that, then n factorial is just gonna be super huge, and you're gonna get a time limit exceeded. So that's a pretty bad brute force algorithm. We'll then explain an O(n) squared solution. So an O(n) squared solution is, not as bad as an n factorial. It's much better. You can go all the way to n around 10 to the 4 / smallish 10 to the 5s. Okay, and it would still run in reasonable time. We'll then give another solution, which is an O(n) log n solution. And whenever you see the O(n) log n solution, you usually think about sorting, and you're right. We're going to give a sorting-based algorithm, which is an O(n) log n solution, and that works, pretty well for n, ranging to even 10 to the 6. It would perform pretty well. Finally, we're going to give an O(n) solution, which is based on hash maps, the data structure. And we're going to see that, that scales pretty well. You can go all the way to 10 to the 8th or 7th if the input allows it. So yeah, hopefully you'll see how the progression goes from an O(n) factorial horrible solution to a O(n) squared solution, which is, meh. And then O(n) log n and O(n) solutions, which are, this one is actually very short. You can write it in 4 to 5 lines of code and very efficient. I think it's pretty cool. And then finally, the O(n) solution is a bit longer, but also uses a hash map and very efficient. So yeah, you can write it even in 5 to 6 lines probably. So yeah, in the next videos, we'll start by explaining the O(n) factorial solution, and we'll go from there. So until the next video, happy coding.